But on to what we did so far, let me just remind you that we started exploring the mathematics and the physics of these quantum spin chains. And here, more or less, on the top you have the mathematics, and on the bottom you have some couple of words about the physics. So we started looking at solutions of bit equations. And there are several regimes. So first, when the roots u are of order 1, and the roots u being of order 1 means the momenta are of order 1, we saw that if they are of order 1, there are complex solutions, and they are very, very well separated by I, with exponential precision. If they are complex, they are really extremely well separated by I. And there was a simple interpretation for the corresponding wave functions. They describe blocks of spins that move more or less together, not strictly together, but localized together. They form what we call a bound state. I think this is a really neat example of a bound state. This is how one should think of a bound state. It's just two particles that are moving together, and they are just traveling together. And there is a contribution of the wave function where this spin down and this spin up are exchanged, but that's suppressed. There is one where this spin down is here, but that's even more suppressed. So normally, all the spins are moving as a block. This object behaves, is a quantum particle, is as much as a particle as a single magnon is, a bit more delocalized. It's not just some finite volume, it's a bit bigger object. But otherwise, it's a particle, another particle in the spectrum of what are the possible excitations of my spin chain. And the possible excitations are fundamental magnons and their bound states. What's the fate of this string as we decrease its momenta and go to roots of order L? Roots of order L means momenta of order 1 over L. As we decrease their momenta, as they become more and more and more delocalized, the separation is no longer I. In fact, we also computed the separation, and now they go to some center of mass position that we could estimate, and then the separation was given by the roots of Hermite polynomial. And indeed, our interpretation was to say that in this limit of low momenta, and if we consider only a few excitations at each cut, only a bunch of excitations, then what we get is kind of a bunch of decoupled harmonic oscillators, one per each mode number, indicating, starting already to hint at some existence of some kind of underlying field theory, a collection of many harmonic oscillators. And we see here that you choose different mode numbers and you get different strings separate, and you get a bunch of decoupled harmonic oscillators, one per mode number. And then we said by words, and we are going to explore it further, that if we further now increase the number of particles in each of these strings, such that now not only the rapidity is of order L, but so is n also of order L, so we put many, many excitations, we start getting some bent umbrellas. Now the dynamics is much more complicated. Now the momenta is L times 1 over L, so it's of order 1, and the energy is L times 1 over L squared, so it's of order 1 over L. So it's not as small as in the previous case. Remember, the energy is sum of 1 over u squared, right? At large u. So it behaves as 1 over L squared for that case, 1 over L in this case, because we sum L of them. So these are what are called low-lying excitations. The physics picture we should have in mind is now not of a spin block moving abruptly, but rather as some spins varying very, 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 very slowly. There should be some kind of field theory associated to it that we will start studying tomorrow, I hope. And the picture that we anticipate is that there should be some kind of analogy between the amplitude of each mode that we excite and how many roots we are putting here, and the mode number that we excite and the mode number of the cuts that we are exciting. Yes?
In the last set of spins, it's possible to get like a topological defect where they can, currently that you've got them winding down and then coming back up the same way they went down.
Yes. Yeah, that's right. Yeah, you can have winding, and it is related to having momentum in the spin chain that is 0 or a multiple of 2 pi. If it's a multiple of 2 pi, you interpret it as winding. Okay, very good. So this is what we saw so far. And today, as I said, or if I did not say I wanted to say, we have a very ambitious day, which is probably one of those days where I will do 1/3 of what I wanted to do. I want to do several things. So one thing we want to do, which is to So as we said, so these roots condense into some smooth curves that we can call cuts. We can say there is a cut here C1, a cut C2, a cut C3, and so on. So there are a couple of things we want to do. The first one thing we want to do is solve with equations in this limit for any number of cuts. Okay. Now, you should have in mind this looks crazy a priori, right? I mean, unless you saw something similar, the first time you see it, it should look like something totally crazy. Now we want, the claim is we want to describe this most general configuration of umbrellas. In other words, we want to take bit equations, expand them when the roots are large, we give these equations here. Are these equations familiar to everyone? It was in one of the tutorials to expand the equations at large U and see that you get this. If they are not, it's just what I said. Just take the equations, expand them at large U. We want to find all solutions to these equations and write, for any number of cuts, here is what the energy is, as explicit as we might be. Okay? We will see how explicit it is, but you see, it's something, it looks crazy. To be able to say, I want 3 cuts, each of them with equal filling fraction, which means each of them with the same number of particles, this one with mole number -3, this mole number 2, this mole number 5. And given that, we want to have a formula that we can put in a computer and get what is the energy of that state. It will be 1 over L times some number, and we want to compute that number. Okay? So this is the mathematical goal that we want to do. And physics-wise is how to recover that from the effective field theory for the low energy excitations around the ferromagnetic state. Okay? So these are 2 ambitious goals, and today we will focus on this one, and hopefully starting tomorrow we will focus on the second one. Okay? And as you will see, it's a bit surprisingly, but this will lead us to a totally different domain in mathematics of algebraic geometry, where we will understand that finding all possible solutions to this problem is the same as finding all Riemann surfaces or algebraic curves of a particular type, as we will explain now. This is one of the things I want to do today, and the second thing I want to do today, which is unrelated to this, is cover a couple of points related to things we have seen before. Namely, some people were a bit confused when we say something like, I have an incoming wave plus this matrix times outgoing wave, and some people were complaining, you have a stationary state, it doesn't look like a time evolution where I prepare some incoming state and get an outgoing state. It looks more like I just have a stationary state with one plane wave and another plane wave and an S matrix in between. So why is this the same thing as time evolution? And this is a question you could have asked in quantum mechanics when we solve some square potential and we write incoming wave, reflected wave, transmitted wave. It looks like a stationary state. Why is this the same thing as saying that I send a wave and it scatters and it bounces back with a respectful time evolution? Okay? So this is what I will do when we will be running out of time, because this is something that people are expected to know in quantum mechanics. So those that know already very well this, they can leave. And I will review this basic thing of how to connect stationary states with time evolution. Okay? But that is the bonus for the when we will be over time. Okay. So let's start by understanding. Any question first? About what is the goal? Okay. So here is how it works. So let's go and find the solution to this equation. So the step number 1 is, and what we are going to do is try to mimic our intuition with the harmonic oscillator. Remember, with the harmonic oscillator, we had a bunch of cuts, a bunch of poles. that then condensed into a cut, and the cut was just square root of energy minus potential. Okay? So let's follow our nose, and now we don't have a quasi-momenta, so let's define one. So let's introduce a quasi-momenta. And let's define it. And let me define it in the following way, and you will see that it's a very clever definition. Let me define P of u to be sum from j equal 1 up to n, 1 over u minus uj, minus L over 2u. Okay? So this is the definition. You see, it looks very much like the quasi-momenta, if you remember, for the harmonic oscillator, where there was some potential and then a sum of poles. Each a pole with residue h bar over I in that case, and here each pole with residue 1. It's my normalization. I could multiply everyone by I and have something even more similar to what we had before. Okay? This is our definition. Now, this is a function that has poles. Okay, now we can start calling them poles. Before I was calling them poles, it was an abuse of language. Now I can call them poles. Here is a function that has poles. And now the claim is that this function, however, if we zoom out and if we are far away from the poles, these poles will become like cuts. And this function P will now, instead of having poles, it will start having cuts at these positions here. The same mechanism as what happened for the harmonic oscillator, we expect it to happen here. Okay? So the idea is that this function now, if we take the number of roots to infinity, this sum just becomes some integral of rho of v dv over u minus v. The integral over what? Over the union of all these cuts. Right? I integrate over all the cuts. Minus L over 2u. Okay? So this this is what it is. Okay? So here we have a bunch of poles, and here these poles became, we took so many that they define some smooth contour, and I'm defining my, my integral over all these possible cuts. Okay? And now let's say we have a cut here, and let me draw the cut horizontally, but it doesn't matter. If it is not horizontally, what I will mean by up and down is on one side of the cut and on the other side of the cut. Just putting it horizontally, it's easier to explain. And let's consider the value of the quasi-momenta here, P of u plus I0, where again, plus I0 means to the left of the cut if you want, and the value here. Okay? And now, let's ask for what is the average and the difference, yeah, of the quasi-momenta on one side of the cut and on the other side of the cut. Okay? So what is the difference? P of u plus I0 minus P of u minus I0. Well, that's a question for you. So I have some density and I integrate along the density, and then I evaluate right above and right below. So what happens when I do that? It almost, you see, this part cancels. L over 2u slightly above the cut minus L over 2u slightly below the cut, it just cancels. This L over 2u doesn't care about the cut. So it's all about this term here. This term here, if you put here u plus I0 and subtract u minus I0, you could think, oh, it also cancels. But it's not true, because we are integrating, and we have that 1 over u minus v plus I0 is equal to principal part of 1 u minus v minus I pi delta of u minus v. Okay? This is just a statement that if you integrate, if you do an integral like this integral is equal to the integral where you open some epsilon or you pick or you pick half of the residue, which is the I pi delta function. Okay? Similarly, if I have with minus, I get a plus here. Right? I'm not sure if the contour should be this or flipped, but I think this formula is correct. Okay? So what happens when we take the difference? The principal part integration, which is the integration where we open a small interval, cancels. And the delta function doubles. So we get the delta function here. When we integrate a delta function, we pick rho. And therefore, this is just up to a sine 2 pi I times rho of u. Okay? So if you give me p, I compute the discontinuity of p, and I get rho. So the density is the same as the discontinuity of p. This is always true. It was true in the harmonic oscillator. Remember when we plotted the density of the roots of the Hermite polynomial, and then we plotted it against the square root, which was the discontinuity of p in that case, and we got the match. Right? So this is the same story. Okay? So this is by definition. This doesn't use any bit equations, nothing special about our spin model. It is just if you define p of x like this, you compute the discontinuity along each of the cuts, and you get the density. Okay? So by the way, just one comment. Suppose this is a branch point, and this is the other branch point. These are two branch points. And then, a priori, when you have a function with two branch points, as we were discussing the other day, you can put the cuts wherever you want. Right? The cuts are not meaningful. You can say, oh, the cut's like this. Whew. Or the cut can be whatever you want, right? And the real cut is this one. And what's special of the real cut versus the silly cut? Right? So this is the silly cut, and this is the real cut. And what's special? The thing that will be special is that if you compute the discontinuity, so you compute p on both sides, you compute the discontinuity here, and you consider the quantity rho of u times du, where du is an element that is pointing in a given direction. And if we are integrating rho of u du, we should be counting how many particles there are there. So the condition that this thing is real defines what is the real cut. Okay? So if you start at a given, you have some density at a point, and you want to ask in which direction du should I go? And you should go in the direction which has the phase opposite to that of rho, to cancel the phase and to get something real. Then you do a small step. Then you go to the next point. You recompute rho. And you ask, in which direction should I go now? And you ask again such that the rho of u times du is real. And you move a next step. And you integrate this and you get the real cut. Okay? Okay, good. So now, so this was the difference. What about the average? What if we compute p of u plus I0 plus p of u minus I0? Okay, so this is the average. Sometimes we define this with a slash, p slash of u, to indicate it's on one side and on the other side, but it's not very important, this. But what is this equal to? Well, now it's the opposite. Now the delta function cancels and the principal part survives. So this is integral with principal part prescription. I don't know which notation you use. I like to use this notation. This is just the same notation. I don't know which one you learn in school, but it's the same. This slash notation, that's why we use p with a slash. This is why this reminds us this. Minus L over U with a 2 here. We don't average, but we multiply by 2. Right? It's not 1/2, it's really the average. And this is what we get. Okay? But now there's something, now we should look here, we should look and see, but wait. This is nothing but the continuum limit of these equations. If I would take these equations and take the continuum limit, by this I mean I replace sums by integrals, we have to be very careful here. Because what are we doing? We are summing over all particles except particle j. So we have to open a small hole at particle j when we are replacing this sum by an integral. Right? Because this is singular when uk goes to uj. And what is the prescription that we get inherited from the correct quantum description? Is that we should not go all the way to k. So we should stop at the last root and start at the next root. So if we do it, if you do the continuum limit of this equation in the continuum limit, when the number of particles becomes very large, becomes exactly L over U minus 2 pi n minus integral with principal part prescription, rho of V over U minus V equals 0, when U is in the cut CK. Okay? Principal part very important, otherwise you don't know how to integrate when U is equal to V. That's the only way this could make sense. So we see something nice, that the average of P on both cuts, which is P of U, P slash of U, is equal to 2 pi, is equal to a constant, 2 pi nk, whenever U is in one of those cuts. Okay? So in other words, when we are at a given cut, here, say on one side of the cut, P of U is equal to pi nk minus I pi rho of U. And on the other side of the cut, P of U is equal to pi nk plus I pi rho of U. Okay? And now the idea is, if a bit intimidating, very simple. The idea is that now we know a lot about this function P of U. This is extremely powerful to tell you that I have a function with a given number of cuts, and I know the discontinuity and the average on the cuts uniquely defines the function. So the basic idea now will be, let's try to list all the analytic properties we know about P of U. We just need the hardest one, which is to deal with these cuts. We just understood that this P will have a bunch of cuts, and we already understood everything about the cuts, the discontinuity and the average on the cut. So now let's find what are all possible singularities of P of U, and then we can give a mathematician. We can just say, give me a list of all functions that have these singularities and these cuts. And the mathematician will give us the answer, or rather he will give us a book on algebraic geometry, which is the subject that solves this kind of problems. We open the book and we make a list of all possible functions P. And once we know all possible functions P, we know we have the information about the roots, and we can read off the energy and so on, which is what we want. And in this way we solve this problem of dealing with this spin chain. So is the strategy clear? Okay, so let's do it. Of course we are not going to ask a mathematician, we are going to do it ourselves, because it's relatively easy. Okay, so the other properties are much simpler. For example, P of U, how does it behave at large U? Well, if you take this equation and expand it at large U, this behaves as integral rho of V dV minus L over 2 times 1 over U. You agree? Just expand at large U, You get 1 over u times the integral of rho of v minus L over 2u times 1 over u. Right? But what is this? What is the integral of the density? This is just the number of excitations. Right? So this is just one of the charges. What does this measure? This measures, what is it? It's the number, okay, this is minus L over 2 minus n. Okay? So we start with everyone up, and we have total SZ component L over 2. And whenever we flip, we change the SZ component by 1, because we remove an up and put a down. So that's the total SZ component. Okay? This is the total SZ component. In other words, by looking at infinity, you see how many excitations you have. You know the length, you see how many excitations you have. Good. What about large u? What about small u? Small u is more interesting. So first there is a singularity. So it is minus L over 2u. I need spacing. Minus L over 2u. Then there is a regular term, minus integral rho of v over v. See?
The integral, is it over all cuts?
Yeah. The integral is over all cuts. Right? Is it clear to everyone? Why wouldn't it be? We have integral over some contour, we expand in u, we get the same contour. So here we get this integral. And note that this is totally okay. There is a 1 over v, you might worry, whoa, what if v is 0? Of course v is not 0, you see the cuts are there, you don't go through 0. You are just integrating over some contours, it's totally fine. This is what it is. And then you continue, and you get, and I forgot once again to do it in Mathematica, so probably the signs are wrong, plus u times integral rho of v dv over v square plus order u square. Okay? But okay, this one I should be able to do it without Mathematica, right? It's just expansion of 1 over u minus v, it's 1 minus x, so it doesn't change sign. We expanded small u, so we put a minus, and then it doesn't change sign. Sorry? Okay. And now, this quantity and this quantity, they look a bit funny, but they are very physical quantities. In fact, this one here, let me show you, is nothing but the momentum of my state. If I have the momenta, you see, this is just the momentum of my state. But now if the UKs are large, this becomes just sum over k 1 over UK for large, which becomes this quantity here. So by looking at the value of p close to 0, if I look at the constant term, I read the momentum of my state. Is it clear? And this one here is just the energy of my state. The energy just becomes that particular one there. Okay? So this is cute. So the idea will be, let's find all possible functions p. And once we do it, once we find a particular function p, we go expand it close to u equals 0, and we read off the energy and the momentum of the state, which is we read off the spectrum of our spin chain. So just a comment, this total momentum of the state is not arbitrary. Indeed, if we take bit equations here, for example in this form, and sum over k, what happens when I sum over k? Well, this sum here is antisymmetric, this sum just vanishes. Right? So I get that L times total momenta equal to an integer. So this quasi-momenta is not anything, but L is equal to an integer. Which we could have gotten this without any computation. All we are saying is that if I translate the full system by L, I get back the same thing. So of course the self-interactions ought to cancel. Just a global rotation of everyone. Okay? So this is just true for any system. It will just rely on the antisymmetry of the S matrix. It's not particular to this expansion or to anything like that. Or rather, I should not write, okay, this n, where this n is the sum over all the mode numbers that we have. Okay? Cool. So this is what P is. So this is what P is. Now, yes?
Is this thing a consequence of the fact that those are the higher charges of the theory? That like I have the charge which is proportional to the first power and then the second power, and then if we had some like higher ones.
That's absolutely true. So if you would expand to higher powers, you would be measuring higher charges of the theory. You would measure what's the value of this Q3, Q4, and so on that we spoke about. That's totally true. So you start seeing that these kind of things are all a bit related. So here we are also introducing once more a new variable u, this u, which is kind of a spectral parameter again. And by expanding this u at particular values, we are getting the charges. So you can ask, is this P of u, can I also relate it somehow to all this R matrix business and transfer matrix and so on that we constructed? And the answer is yes, it's possible. I'm not going to explain it in this way. But if we did, we would see that this P is related to the eigenvalues of that transfer matrix. So this U is very much related to the U we saw before. Okay, so all these subjects are full of connections. I don't have time to explore all of them, but it's a good observation. Indeed, it looks like it should be related, and it is. Good point. So now, let me tell you why this P of U, even though now we know a priori everything, you see there are no more singularities, right? P of U, by definition, it can only be, the only thing we had to check was infinity, 0, because there was explicitly 1 over U, so we better see what happens close to 0, and what happens close to the cuts. Otherwise, by definition, this is an analytic function otherwise, right? You have your P. If U is not close to any cut, you can move around and it's totally smooth, nothing happens. So we analyzed, in principle, now we should be able to know what all P of U's are. We just say functions without singularities, we just discuss, we just prescribe the asymptotics and so on, it should be everything we have. Nevertheless, this P of U is still a bit complicated. Let me tell you why. Then the reason is that this P of U describes an infinitely shitted Riemann surface. Okay? So it's a tough object. So let me tell you why. So let's start on the defining sheet. So let's say we define this sheet, and now we have some cuts here. Right? Actually, just to simplify the picture, let me draw the cuts horizontally instead of drawing them as arcs, because it's just easier to draw if they are horizontal. You can draw them in your paper if you are more skilled with I will draw them horizontally. They can be arcs, doesn't matter. Okay? Good. So let me remember how this goes. So we have P, we go here, P, here, pi. Okay. So what's happening here? So let's suppose we come from infinity, and we want to enter this cut. Okay? So when we enter this cut, what happens? Well, when we enter this cut, we go to the second sheet. So we go here, and now we are here. Okay. Good. So if we call this value here before crossing the cut P, right after crossing the cut, if you enter the cut, here you have P. The function is smooth, it's just analytic continuation. I'm just going through, it's P, it continues P smoothly. On the other hand, on the other side of the cut, we know it is not P. On the other side of the cut, here, we know it's 2 pi n minus P. Okay? So we know that if we, and what is this value here? The value here is what I would get if I would come from the other side of the cut. You see, because this side smoothly connects here, and this side smoothly connects here on the other side, right? I have a cut, and I enter here, I go here, and I enter here, and I go here. Is it clear? The things are smooth. I go, I come here. I go, I come here. Okay? So it means that one second. So I have here, I have here. So here again, at this value, we are at 2 pi n minus P. Okay. But then it means that if I take this value here, right? So I take this value here, and now I go here to where this other cut would be. Okay? And I get here, I start with this function here, which is 2 pi n minus P, and I get here 2 pi n minus P. Whatever the function is that I take 2 pi n minus P and carry it all the way here. Which is not 2 pi m minus P if this cut has mode number n and this has mode number m. Which means that if you go through this cut here instead, you go to another sheet which is not this sheet. This is all I want to emphasize with this complicated explanation. Is that what the equations are telling us is that you can go through this cut, you go to another sheet, but if instead you go through this cut, the way you should draw it is that there is another sheet. And you go to yet another sheet. And this cut is still there for this sheet, but if you now go over, you go to another sheet. And in principle, you get a beast, which is just a connection of infinitely many sheets. At each sheet where you are, you have the cuts at the position of the roots. But when you go, because of these funny mode numbers, the monodromy is not trivial. If it was not for these mode numbers, whenever you would cross the cut, P would go to minus P, right? And if you have two cuts, and P goes to minus P, then you go here, and minus P goes to P, it's fine. But if P goes to 2 pi n minus P, and then I go, and I get 2 pi m minus that, in the end I don't go back to P. I go back to P up to n minus m. You see? So if I do a cycle going through the two cuts, it's not consistent with going back to the same position. Right? So if I do a path that goes inside both cuts and comes back, because I change from P to 2 pi n minus P and then 2 pi m minus that, in the end I end up with P plus m minus n. So there is a shift of P. And then if I continue doing this, I keep shifting P by more and more, so in fact, I will end up with an infinitely shitted Riemann surface. Yes? They do. We know how to cross each cut. We know that as we cross the cut, we get the density and so on, but it's a big mess. Okay? So the problem is that we get an infinitely shitted surface. Okay? Again, the idea being that if you cross the cut, P goes to... If you cross the cut and then go back to the same position where you were, it's not just cross, P goes to P, but then you go to the same position where you were, right below. Then P goes to pi n minus P. Then you go here, do the same thing, cross, and then go to the same position. So at the end, this might be an easier explanation. If you go like this, you don't get back to yourself, but you pick an extra monodromy. So it's not compatible with saying I go to sheet 2 and I come back to sheet 1. So it is not a two-sheeted surface, it's an infinitely sheeted surface. As we are going around, we know how to go around. You see, we know you can go around, and I can tell you, okay, you will not go back to P, you will shift by an integer. But it's kind of complicated to label all these functions that have all these fancy monodromies. Even if I ask you to find me one such function with two cuts, you will struggle a little bit. And you will have to go to hyperelliptic functions, Jacobi functions, and so on. It's a big, big mess. But it can be done. We will do it in practice. We will be constructing them, but in a clever way. So our goal here is we are almost there, but we need one more important idea. We need to reduce these infinitely many sheets to something reasonable. Let's say to 2 sheets. That would be perfect. If we could simplify the problem and just have 2-sheeted surfaces, those we know very well how to deal with. It's a much simpler mathematical object. So there are 2 options to do it. We are going to use the second one, but let me tell you both of them. There are 2 simple options. One is to define lambda of u as e to the I p of u. And the other option is to use the derivative p prime of u instead of using p of u. Okay? And the reason is very simple, is that because what happens for this lambda of u? Well, for this lambda of u, here on this side of the cut, I have lambda of u. Then on this side of the cut, I have 1 over lambda of u. Because in the exponent, these 2 pi n's I don't see. So if I have p and 2 pi n minus p on the other side, that just means lambda and 1 over lambda. So now it's pretty clear what happens. So now, indeed, if I do a path like this, it's totally fine. If I do a path like this, all that happens is that lambda goes to 1 over lambda goes to lambda. So this is a 2-sheeted Riemann surface. It's a 2-sheeted Riemann surface where we have our cuts. Where here we have lambda, and right below we have 1 over lambda. You see that I wrote right below, but on the same side of the cut. Of course, again, if I cross smoothly, I get the same value. Okay, so this is the sheet lambda, and this is the sheet 1 over lambda, and cuts flip lambda to 1 over lambda. Now this is much simpler. Now I just need to find functions lambda that have 2 sheets, but the problem is that the analytic properties, when P had nice analytic properties, because we put it in the exponent, this lambda has essential singularities. It is exponential of poles. It's kind of nasty. Okay? But it's the simplest thing you could come up with. You just, I don't like these integers, I exponentiate because the integers disappear. But even simpler to get rid of constants is to take derivatives. If I take derivatives, I take the derivative of this equation, all these constants go away, and I get P prime goes to P prime. So derivatives also work. right? So we have P prime, it goes right? P prime goes back to P prime, so it's the same story. We have a two-sheeted Riemann surface, where here is the surface for P prime, and here for minus P prime, and we have some cuts where we flip from P prime to minus P prime. Okay? And this is much better, and we can just go back here. And now let's say we want to find the function P prime, and what are the asymptotics of P prime? Well, P prime of u, I just expand from there, behaves as L over 2 minus n over u squared plus dot dot dot. See, I just take the derivative. And here I learn that P prime of u behaves as minus L over 2 u squared. The momentum gives us 0. It's a constant. And the energy gives minus the energy of the state times u, times the energy, sorry, plus order u. We take derivative. Okay? But now it's very simple. Now we just want to have a function that has these prescribed analytic properties at small u and at large u, and that has a bunch of cuts. And on the cuts, we know the discontinuity and the average of P. Okay? Okay? And we also know that close to a cut, if I have a cut, here, P prime of u will behave as 1 over square root of u minus u star, if this is the value u star, since P of u will behave like square root of u minus u star. So we know the analytic properties close to each of the branch points. We know the analytic properties at infinity. We know the analytic properties of 0. And the beast we are dealing with is just a two-sheeted surface. So I can immediately write down what the solution is. Okay? This is really the kind of problem that if you open a book on algebraic geometry, people will tell you. I want a function defined on a two-sheeted Riemann surface with these singularities and so on and so forth. And here is the answer. It's very simple. Let me tell you what it is. The answer is, let's write the answer and see that it's the only thing we could write. P prime of u equal to, well, it can have a singularity, so let's put a singularity here. Product j equal 1 up to 2 times the number of cuts, u minus uj. You see there is 2 branch points per cut. Let's call them uj star, not to confuse with the bit roots. These are the position of the branch points. It should have a 1 over u squared singularity when u goes to 0, so let's put here a u squared. Now when u goes to 0, it has a singularity. And upstairs, it can be a polynomial of u, which can start cj u to the j from j equals 0 up to which power? Well, we cannot put the power too high because otherwise at infinity it would not decay fast enough. It needs to decay as 1 over u squared. So downstairs it decays, it goes to 0 as u squared plus something. So we can cancel this something, that's the most we can do. So we can go up to the number of cuts. Okay? So, in sum, for k cuts, we have 3k plus 3 free parameters. So the problem is not solved. We still have the free parameters. But we are a good ways towards solving this problem. We already reduced, I counted wrongly. Let's count correctly. Can you fix this counting? So let's see. We have 2k, I said the 2k positions of the branch points. And how many there are here? Yeah, so it's not 3k plus 3, but it's 3k plus 1. Okay? But you see that this function here, it automatically has the desired properties. See? When I cross each cut, the square root flips sign, so p prime goes to minus p prime, that's good. It behaves as 1 over square root close to each cut, it's good. It has the right asymptotics at infinity, it has the right asymptotics close to u equals 0. So this has the potential of working. Okay? So this is what's called a meromorphic differential on the Riemann surface. So this is a differential on the Riemann surface. And why do we call it a differential? Because if we want P of u, what do we do to get P of u? Well, if I want to get P of u, what I do is start from infinity and construct P of u by integrating all the way from infinity up to u, P prime of v dv. So I take my point and I integrate it and I get P at a given point. Okay? Now, this is all very abstract, so now we are going to finish solving the problem and applying it to a particular example. But I want to ask if there's any question here. Yes?
Because the U, J star are the two endpoints of the cut.
Yes.
And if it's a solution to basic equation, say, for cut, you have 2 points, right?
Yeah.
It should be conjugate to each other.
Right, so you have the real and the imaginary part for each of them.
So you're saying it's 3k plus 1 real, right?
Yeah. Yeah. So it's, yeah. That's right. So what he's pointing out is that when you have the cuts are complex conjugates, so we can have U1 equal to, say, capital U1 plus I V1. Then U2 will be capital U1 minus I V2, and so on and so forth. Minus I V1, and then so on and so forth. So they come in pairs, it's true. The branch points are something and complex conjugate, but 2 branch points still come with 2 parameters. Okay? So 3 real parameters. This P prime is a real function, so these CJs will be real. Okay. So now, let's go and try to understand how could we fix these parameters. You see, if we could fix these parameters, we would be in business. Suppose I give you all these U's and C's. What do? Well, you do something very simple. You just put it in mathematics and do series around U equals 0, and you read off the energy by looking at a constant term. Right? So if I can fix all these constants, then I just expand it at 0 and read off the energy. Do you agree? So we reduce this to a very well posed problem of finding these 3k plus 1 parameters. Can I go on here? Can you read if I write here? Yeah? Even you? That it's not too tilted, it's okay? So now the idea is the following. We start with our cuts. Okay? And the first thing I want to say is that if I start with my points and integrate and I get P, I better get the same thing, otherwise things are not okay, if I go around and compute doing a different contour. So this is consistent if and only if the integral, the difference between the two, which is the integral around this cut, okay? And if this is a cut C1 and this is a cut C2, this is what is called an integral of P prime of V dV around the so-called A cycles of the Riemann surface. A cycles are these cycles that go around the cuts. Okay? So this would be A2 is equal to 0. Okay? For K equal 1 up to the number of cuts, capital K. Okay? So this gives me some conditions. I plug this, I do all these integrals around these cuts, and I impose that each of them is 0. Now, you might think, and it's more or less correct, that this gives you might think that it gives you K conditions, but it's K minus 1. Can someone tell me why it's K minus 1 and not K?
I was actually going to say, I think there are only K minus 1
Yeah.
A cycles.
Very good. Why? Because there are only K minus 1 independent cycles. If we think in terms of a Riemann surface, if we have these two cuts, if this is 0, I can just blow this contour and map it to the contour around C1. And if I have 3 cuts, if I know that C2 and C3 is 0, I can combine the both and blow the contour and get that C1, the contour around C1 is 0. So there are only K minus 1 conditions since P prime goes like 1 over U squared at infinity, and therefore there is no singularity at infinity, so I can just blow the contour, and if we have, for example, like 3 cuts, if I know this and this is just equal to minus this. Okay? So the A cycles are not all independent, and if I know, if I impose it to K minus 1 of them, then I'm guaranteed that if this is 0, this one is going to be 0. So there are K minus 1 conditions. Okay, so we already got from 3K minus 1 to 2K plus 2. Let's go on.
So these give you complex.
Sorry?
So that you go on to K plus 2 because these give you complex conditions. I'm trying to see how you got from 3K. You're saying you get from 3K.
I subtract 3K plus 1 minus K minus 1. It gives 2K plus 2. 2K plus 2. Next, we impose that if I integrate now from, if I do the following integral, let's write it, integral from infinity up to U plus I0, that I start here and I integrate up to here, okay, plus the integral from infinity to U minus I0, I start here and I go now here. Then what do I get? I get P at one side plus P on the other side. Right? By definition, I integrate P prime, I get P. But the average of P on both cuts is exactly an integer. So if I integrate P prime of V, this is just 2 pi nk when I go to the cut K. So these are called the B cycles of the Riemann surface, and they give K conditions. So this is where bit equations are coming in. They are telling you that if you integrate from infinity to one side or to the other side, that you get an integer. This is equivalent to bit equations. Okay, K conditions. Finally, we have that I can measure how many excitations I put on each cut. So I have the condition that there are nj roots. And what is nj? It's just the integral of P of U du around the A cycle. Right? Because P is just a pulse. So by doing a contour integral of P of U around the A cycle, I just count how many roots there are on this particular cut. right? But what is this integral if I want to translate it into something? So this is the same as saying that nj, if I integrate by parts, is minus the integral of p prime of u times u du. Okay? And this gives me k conditions. Okay? So we got k, k, k. So the 3k we got rid of. But let's check if we got 3k plus 1 or if we are missing something. And we are missing something. We are missing two constants. Right? K plus k minus 1 gives 3k minus 1, not 3k plus 1. Okay? So up to now, can I continue here or this is a stretch? Now it's a bit tough for you, right? So I can move some other place. Okay. I think that part in the top is clear, right? We have P of U, the average, and so on. Yes?
I think there should also only be k minus 1 B cycles.
It,
Just your genus is k minus 1 if you have k types.
no, that's I don't think that's true.
I mean, every cut you add is just like linking another tube, right? If it's two sheeted.
It's true that you can relate this condition using let me keep discounting. You would relate discounting using some Riemann bilinear identity to a different parameter that I'm not counting. We can discuss at the end. But you will see applied on an example that I do need this condition for one cut, for example. Okay? But then I can also tell you how I could replace it by something else which would agree with your counting. Okay. So we can, sorry? Yeah, I know. I'm going to use it now. I just don't like to have hidden blackboards. Okay. So now, two constants missing only. So we're almost there. Only two constants missing. So what are we missing? Well, we didn't study yet the singularities at large U and small u. Okay? Now, at u going to infinity, we get nothing. We get nothing new for the following reason. We get nothing new because the asymptotics that we get, this L over 2 minus capital N, this N is just the sum of the Nj for j equal 1 to capital K. Okay? So if you think a little bit from that point of view of integral of p prime of u du, this capital N, if I have my cuts, if I take the pole at infinity, so if I already computed all these cycles, okay, this integral of p prime of u times u du, right? I blow the contour now to infinity, and this is, of course, if I blow it to infinity and use the asymptotics, this is just L over 2 minus n. Sorry. That's true, but I should put u equals 0 inside. I put the contour that encircles everything, then I just blow it up. Right? I just put a contour that encircles everything. But on the other hand, this contour, I can, instead of blowing it up, I can integrate around each cut and around each singularity. And this cut gives n1, this gives n2, this gives n3 by the conditions that we imposed. And this integral around u equals 0 gives L over 2. So all this gives is that this is automatically satisfied with n being the sum of the excitations that I put at each cut. Okay? So this will automatically work. It will just tell me that the number of excitations is the sum of the number of excitations at each cut. So it's again telling you that if you know already each cycle, you can blow up and get the cycle at infinity. Okay? So this gives nothing new. However, u equal to 0 does give something new. Namely, we have to impose that p prime of u goes as minus L over 2 times 1 over u squared plus 0 times 1 over u plus ta ta ta. And it's important because from our ansatz, it's clear that you have a double pole, but it's not obvious that you don't have a single pole. But we must cancel the single pole, otherwise we get a logarithmic singularity for p of u that was not there, obviously, from our definition. Okay? Or, in other words, we just said that there should be a 0 there. And this gives us the two missing constraints. Okay? So, to summarize, you write this ansatz, and you impose these 3k minus 1 integrals, plus these two conditions, you fix all the constants. It's powerful. Now you fix all the constants, and what do you do with this? You now go one term further, and here we rid off the energy. Okay? Okay. So any question here? So now I have two options. Option 1 is stop. Actually, it's 3. Option 1 is stop here, and we continue tomorrow. It's kind of a pity because I wanted to clean this today. The other option is now show you an example. This looks all very abstract. Let's take the simplest example where you have one cut. And let's try for one cut to see how it works. For one cut, we have 4 constants to fix. How do we fix these 4 constants? Just on the example of one cut, where I can open Mathematica and just do it for you and compute the energy, and you see how it works, and you would understand how to do more cuts. The third option is to tell you why when I have incoming plus outgoing wave, this is really an incoming plus outgoing wave in quantum mechanics. Or I can do the last 2, but then we will go to half an hour more, which I don't care, of course. So what do you prefer? Option 2, which is do the example of one cut. So who votes for option 2 of do the example of one cut?
Like just that?
Sorry?
Just that?
Start by that, and then we decide at the end we do a next vote to see who is already. Sorry?
I have a suggestion maybe for others before they start voting to consider. If we do only the third option, then when you always write the summary on the blackboard in the beginning of the lecture, it would be nice for everybody to, we will have it like everything on one place, and then you do the example to...
But right now it's more or less in one place, no?
Yeah,
I mean,
sure.
as you prefer. Okay, so do you want to revote again? Who wants example number 3 or example number 2 or option number 1? Option number 1. Stop here. Sorry. Option number 2. Do one cut. Option number 3. Do incoming and outgoing waves. Okay, we will do option number 2. Sorry, I think. Bah. Can I have the projector and this kind of thing? Right. Okay, so while this warms up, let me just point out that, for example, in practice, a simple way of implementing this condition here, right? A simple way of implementing this condition, we can choose any point. We can choose any point on the cut. This point, this point, this point, this point. But choosing the last one is kind of a clever choice. Because what's special at the last point? You know that the quasi-momenta here on the cut is a density plus an integer. But the density vanishes at the endpoints. So another way of saying is that at the endpoints, the quasi-momenta is just pi times n. So I can impose that I start from infinity, I integrate up to the endpoint, and I get pi times n. That's how we in practice are going to do it. So what is P prime of u? Well, P prime of u, we start with our ansatz. And let's start. So we have 1 over u square. And then we have square root u minus the first branch point, which, as your colleague proposed, let's parameterize it with the real and its imaginary part. So we have one cut. One is at a minus ib, the other at a plus ib. Okay? And then upstairs, we have a constant times z plus another constant. Okay? Because now, you see, this goes as 1 over u squared at infinity. This goes like 1 over u squared at infinity. It goes as 1 over u squared at 0. It has all the right. The polynomial is at degree 1, as we said, for one cut. Okay? Then we expand now this pp of u for u at infinity, close to infinity. So we get that at infinity it behaves as c1 over u squared. Okay. And what should this be equal to? It should be L minus, it should be this, right? L minus m over 2. I always use m instead of n because n for mathematics is numerical, right? So this is what we should get. You agree? I mean, here I'm computing the derivative. We did it in the blackboard. I could use the result, but I don't want to do a mistake, so I subtract. Okay? And I say, let's find what is the constant that gives this. Okay? It's kind of clear. The constant will be precisely related to the number of excitations. And we remove the bracket by putting a 1 there. So this is our first replacement. Okay, so we already know one of the constants. Okay? Then, what about the other constant? Now we expand instead of infinity, we expand around 0. Let me show you. And you see there is a u square, and there is the 1 over u. And as we said, the u square we are happy with, but we are not happy with the u. So we want to cancel this single pole and be left with a double pole. So we get these two conditions, which were the last two that we wrote. So let's impose this, and this should be equal to the derivative of this, right? Now it's just L over 2u. And now, let's solve these two conditions now for C0 and A, say. So now we get this replacement. Okay? So we know what C1 is, we know what C0 is, and we know what A is. Okay? So now let me just remove some square roots. Okay, so I just took out some square roots of L square. So this is our second replacement. So again, if I now look at P prime of U, we have 1, 2, 3, 4 constants, but we already have 3 replacements. Okay? So now all we have to do is integrate P of Z. And this is what P is. So you see, P is more complicated than than P prime. P prime was very nice, but P is already a bit more complicated. And what do we impose? We impose that if I integrate P prime all the way from infinity to the branch point, when I get to the branch point, I should get 2 pi n, I should get pi times an integer. Okay? So we will impose that when I integrate for this simple case, we just impose this condition, or even simpler, we just say now we have just one cut. And if I go all the way from infinity here, at this point, P is equal to pi n, right? Because it's I plus I times rho at the branch point, which is 0. So I just need to integrate P, and now I compute this integral. Let's call this integral in Z, or P, to be even better. Okay? And we want to compute, on the one hand, what happens at the branch point. So when Z goes to A plus BI, so this gives this. And we can simplify a bit better. On the other hand, we want to expand this. Why Z? Why Z? Because I integrate in Z. Let's integrate, let's use variable U, you prefer. On the other hand, let's compute this, the other endpoint. You see, you could ask me, sorry, let me explain a bit better. You could ask me, why didn't I integrate directly here from infinity to A plus BI? It is just that Mathematica is very bad at doing definite integrals. She's much better at first integrating, and then I subtract the 2 endpoints. So it is just a question of helping her a little bit. So we compute the integral, and then we expand at infinity. Okay, so this is the value at infinity. And what we want to do is compute the difference of both. So the next to the last minus the last result. This is what it is. It looks a bit messy. We replace the replacement 1 that we already have. We replace the replacement 2 that we already have. Something is fishy here. Sorry. Here I should replace 1 and solve when I already find R1, then I have this. Is it clear? I just replaced R1 that was already solved when I find for the second constant. So then we get this, we simplify. Okay. Much better. And what should this be equal to? This should be equal to pi n. Okay. And now we solve for B. And this is our third replacement. Okay. Now we can conclude. We have this, we replace 1, we replace 2, we replace 3. So here is our quasi-momenta, the function totally fixed. So this is our quasi-momenta, P of U. And now we just do what I said. We just take P of U and expand U close to 0. And we get this. And this here is the energy of the state with one cut. Yes?
L here is the number of spin. Like
L is the length of the spin chain, and M is the number of excitations, which is of order L. So we can write this. Let's write this in a better notation. Let's take this quantity. And let's say that m is a fraction of L. We flip a fraction of L. So let's call this fraction alpha times L. And then simplify. And what do we get? We get a simple function of the filling fraction. You see, this is the proper way of doing it. Times 1 over L. This was exactly what we said. The energy of this cut configuration should be of order 1 over L times a particular coefficient that should depend on how many excitations you are putting and so on. And this is exactly what we are finding. We just solved it for a single cut. And let's see. For a single cut, we said we have no condition from these A cycles. Okay? Because the last one is because only one, because there's no independent one. From the B cycles, we got a single condition from integrating up to the branch point and getting pi n. And from this one, we got k conditions, but we never used it because, as we saw, we can trade one of these k conditions by the asymptotic at large U, as I explained there. And that's what we did instead. We imposed large U asymptotic, which is simpler than integrating around the cut. So the only integral we did was really this B cycle that gave us, was how the information about the mode number n was kicked in. So there is a very simple dependence on the mode number n, some simple dependence on the filling fraction. You see, if you put alpha going to 0, you get 0, which makes sense. You don't put excitations, you get 0 energy. As you are increasing and putting more and more excitations, this is growing. And it's symmetric. If you put all excitations, it's also 0, which is also makes sense, because if you put all excitations, you are again describing a state where everyone is, you just flipped it upside down. Okay? So now you could imagine you write a more general ansatz now with 2 cuts, and you do the same story. The beginning is exactly the same. Now the tricky part is this one here where you have to integrate. Okay? Because now, if we are going to integrate something, let's just see if Mathematica can do it. So imagine I have to integrate and I put an extra cut. Okay? And this I should change. Okay? So suppose I do this, and now I want to integrate. Now I'm not sure if Mathematica will do, but this gives elliptic functions, incomplete elliptic functions. So this is what you need, because you need a complicated function, because now you have 2 cuts, and you need to get, yeah, she did it. Okay, this doesn't look like incomplete, but now, you see. Elliptic f's of arc sines and so on. This is what it is. This is P. If you want to try to parameterize these crazy functions and find P, good luck. You see, it's not a good idea. P prime is just a rational function. P prime square is a rational function. You cancel square root. It's a beautiful rational function. All we have to find. So P prime square, awesome. Just simple rational function that we have to find. P is a big monster because we have to cross cuts, get these monodromies. It's an infinitely sheeted Riemann surface. This is what these functions are. But okay, you can deal with them. Now you can compute these elliptic functions at infinity minus at the cut, at infinity minus the other cut, impose that they give integers, fix all the moduli on this Riemann surface. It's more complicated now. And then you will get the energy of this 2-cut solution, which will be given by some Jacobi elliptic functions. And then you can go to 3 cuts, 4 cuts, 5 cuts, and this is a totally explicit solution, as you see. That if you are happy, for example, with solving numerically, just integrating numerically from infinity to the branch point, you could in principle implement and find the energy of a 5-cut solution. And if you imagine now trying to solve bit equations with 5 cuts, take the number of large roots and so on, it would be, of course, totally unfeasible. So we are making progress. We simplify the problem. We reduce the problem of finding the spectrum of low-lying excitations of the Heisenberg spin chain to the problem of finding 2-sheeted Riemann surfaces, or also called 2-sheeted algebraic curves or 2-sheeted hyperelliptic curves. These are all synonyms. We are reduced the problem to finding 2-sheeted hyperelliptic curves with well-prescribed analytic properties, which is a problem that is solvable, as we saw today. You solve this problem and you get you will get this. Then the question is, could all this story with all these cuts and all these algebraic curves and so on, come from a completely different point of view, starting directly from the effective theory for these slowly changing spins. So now we keep this result on the back of our mind. We know where we should aim. We should aim at these Riemann surfaces. And tomorrow we will change gears completely and start studying effective field theories for slowly changing spins. We will go, turn the wheel, find some effective description, take some classical limit, and we will end up with the very same algebraic curves, thus showing how classical meets quantum in this particular context. Okay, so this ends option 2. So who has energy to see why wave packets, why an incoming plus outgoing wave is an incoming plus an outgoing wave rather than just a stationary state? So who already knows the answer to this? Because, I mean, I was telling a friend of mine, a collaborator of mine, oh, by the way, I have never thought about this point. I'm going to explain it in the lectures. And he was telling me, come on, how come you didn't learn it in school? So apparently some people know it. Some people learned it in school. I have never thought about it. Some of you guys came to ask me and I worked it out. But so is this familiar stuff to most people? Why, if I have a stationary state, this tells me about the time evolution of an in-go state going to an out state? No? Should I explain or explain tomorrow? Who wants to explain tomorrow? 1, 2, 3, 4.
I guess if people are having to leave, then maybe we should go up for this.
Is there a tutorial in the afternoon? No. So who wants to do it now? 1, 2, 3, 4, 5, 6, 7, 8, 9. So now, you wanted to know about this. Did you work it out? No? Okay. So let's start. Let's at least start. And I just want to this is also called the finite gap method.
So this doesn't work for... So when you said it's the finite gap method, how does this go when you're looking at if you go down to zero gap? I mean, sorry, in like a gapless system.
No, I mean, finite gap method is the name of the method. We should the name of the method is related to the fact that you have finite cuts. It's not related to being gap target. Okay, so let me start by reminding you about something simple concerning wave packets. So this first part we do in Mathematica, and then we go to, and then we will we'll go to the Blackboard. So what is a wave packet? A wave packet is you start with a plane wave, e to the IP, x minus x0. So this is your plane wave. And what is the time evolution? The time evolution is minus I p squared over 2. This is the energy times t minus t0. Okay? This is if you start at a given time t0. And what do you do when you prepare a wave packet? When you prepare a wave packet, you say that my momenta is centered around some momentum p0. So you put some Gaussian. If you want it to be normalized, even though this is totally irrelevant, you can put some normalization. Okay? And then what you would do is you would integrate this over p. Okay? So you integrate it over p from minus infinity to infinity. This is so that Mathematica doesn't worry if alpha is real or not real and so on, so that she doesn't scream. So this is what our wave packet is. Okay, now, we can compute the integral, but we don't need to compute the integral to understand the physics of what's going on. So the integral just gives some Gaussian. It's an integral of a Gaussian. It gives back a Gaussian. Okay? But we don't need to understand what is the integral to understand what's going on. This integral, where is it localized? It's localized at the values where the phase is stationary, where the phase is not changing. Right? So the momenta is localized at p equal p0. So this integral is localized at p, sorry, at p equal p0, for the values where the phase is not changing. So we take derivative with respect to p, so we get x minus x0 minus p t minus t0 equal to 0, when p is equal to p0. Okay? So this is where the phase, the derivative of the phase is not changing at p equal to p0. This is what we expect that this integral is localized. And what is the interpretation? We have a particle x that starts at x0 and moves with some velocity for time t minus t0. So it's just a particle moving. Okay? So let's just confirm this intuition. Of course, it's going to work. Our probability amplitude for finding the particle is just the wave packet times the wave packet conjugate. So let's put the wave packet conjugate. So if you have a complex AB replaced by A minus BI, this is just same as conjugate. Times the wave packet, so this gives the wave function square. And we full simplify. Okay, and of course, we get a Gaussian, and where is the Gaussian? It's exactly at what I said. Okay? So, okay. If something is basic, typically you get it right. So, indeed, it's localized at a trajectory we set. So let's plot this, just to show you how you can do some nice plot. So let's plot this. Let's say we replace some numbers. So we replace alpha to be, say, 10. We replace t0, the starting time, by 0. x0, say, by 10. We start at position 10. And velocity by minus 1/2. Okay? And then we say, let's plot the first function, which is the probability, where we replace these numbers. And the function 2, let's plot the trajectory that we expect it to be. So what's the trajectory? P, the position, we expect it to be P0 times t minus t0 plus x0. This is the position, time t. And then we want to plot this function where x goes to this value. So this is a line. It will become clear what I'm doing now. Numerical. Okay? And then we just do a plot. We just plot this function for x minus 40 to 40, t 0 to 40. I just want to emphasize a simple point. Let's put a few points so that it becomes very smooth. Okay? So this is the plot of the wave packet. I'm not going to show you yet because I want to superpose it to the plot of where we expect the particle to be. Where do we expect? We expect the particle to be at this parametric plot 3D. We plot this function f2 from time from 0 to 40. And we can put some plot style. Let's put this to be thick and red so that we can all see properly. And then we show, did I do a mistake?
Yeah, you got 2t, t0.
And then we show the plot 3D and what we expect. Okay, so we see that here is the wave packet. You see? It starts very well, then it spreads out, it diffuses a little bit, and it goes, you see, along this trajectory as we expected. Okay? And if I increase alpha, so if I put alpha equal 50, then it will be more peaked and it will spread out a bit slower, you see. Now it looks more like a wave packet for a longer time, whereas if I put alpha smaller, it will diffuse faster. This is just to remind you, you see, now it starts very well, but then it delocalizes a bit faster. Okay?
I guess you can't check, but is the red line actually sitting at the maximum of the curve?
Yeah, it is. Good. So this is what a wave packet is. And now, with this in mind, we are going to go to the example we want. And can we raise this? And now I'm going to explain how... can we please raise this thing? And now I'm going to explain to you how do we understand this interplay between I can probably do it here. Let's see. Ta 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 ta. Or there. Good. Thank you. Okay. So any question on what is the wave packet? Okay, this you all knew very well, but you probably were not very used to starting using these wave packets to get some intuition about what's happening when you have now particle scattering. So now let's try to do it. Let's start with our wave function. Okay? And let me say that I convoluted, because these are plane waves, but what I want more realistically is to have incoming wave packets. So I convoluted with some Gaussians. So I write the following. I write integral dp1 dp2 e to the minus alpha p1 minus k1 square minus alpha p2 minus k2 square. Okay, then there is the time evolution, e to the I, e to the minus I, epsilon of p1 times time, minus I, epsilon of p2 times time. And then we have the wave function, okay? And then we have our wave function with momentum p1 and p2 at positions n1 and n2. Which I remind you is e to the I p1 n1 plus I p2 n2 plus S matrix times the wave function swept. p2 n1 plus I p1 n2. Okay? But now we see something nice. Now we ask, where is each plane wave localized? Now we take the two plane waves and ask what is happening. And we see now these plane waves will be localized at, we take derivative with respect to p1. So what we get? We get n1, the first one, derivative with respect to p1 gives n1 minus epsilon prime of k1 times t equals 0, and from derivative with respect to p2, n2 minus epsilon prime of k2 times t equals 0. And the second plane wave, the second wave packets will be localized at n1 minus epsilon prime. Now you see that the derivative with respect, or I can write, the derivative with respect to k1 now gives p2, n2, sorry, n2 minus epsilon prime of k1 times time equal to 0, and n1 minus epsilon prime of k2 times t equal to 0. Okay? Just where the two wave functions are localized. But now, we recall, let me recall, remember it's very important that here n1 is smaller than n2. Okay? Now, from these two, I can compute the difference and write that n2 minus n1 is equal to time times epsilon prime of k2 minus epsilon prime of k1. Whereas from these two, I get that n2 minus n1 is equal to time times epsilon prime of k1 minus epsilon prime of k2. Okay? And now we see something very cute. So first of all, this is what you know very well, this is the velocity. This is just a statement that a particle is moving with some velocity, which is the derivative of the dispersion relation. This is what we see here. But then we see something interesting. We see that this quantity here is positive. Okay? So did I do it correctly? This 2 minus, yeah. This quantity here is positive. So suppose I take my velocity v1 to be positive and my velocity v2 to be negative. Okay? So my velocity 1 is positive, my velocity 2 is negative. So then this quantity here is negative. Right? Because it's negative minus positive. In fact, all that matters is that this one is smaller than this one. So this is negative. So these equations only have a solution if time is negative. Okay? So this, because n2 minus n1 is positive. So this is only there for t smaller than 0. So if you go to negative t, if you go to positive t, you don't see this wave function. And this one is the opposite. Now this one is positive. This is positive. So this is here only for t bigger than 0. So this is what we wanted to show. We have a wave function, and what's the evolution? It starts at minus infinity looking like just one plane wave. This is where the wave packets are localized. What about at plus infinity? It's the opposite. It's only the second plane wave that contributes, and what's the relative coefficient? It's S. Okay? So the conclusion is that we start at t equal minus infinity with one plane wave. And as we evolve, we get S times at t going to plus infinity, the second plane wave. Okay? So we see that when we convolute with these wave packets, the statement is that when you have an energy eigenstate and convoluted with wave packets, as you go to the past, the terms that you typically call incoming, you have the right to call incoming. They are the terms that are not suppressed. And when you go to the future, the terms that you would call outgoing are the terms that you have the right to call outgoing. Those are the terms that survive. And the relative coefficient between the two, we called S, and now we have even more the right to call it S. We already had before. We were already seeing that the equations were telling us that as we scatter a particle around, we get the phase and so on. It already looked like an S matrix, but this is how we understand it in real-time evolution. Okay? And now, given that we did this, let's see what would happen, which is kind of nice, because if we would have 3 particles. If you have 3 particles, now it's very simple. You just prepare 3 particles. Okay? And what is these 3 particles? What would you write? You would write integral dp1, dp2, dp3. Then there will be some Gaussians. I'm not going to write. And then there is the time evolution, e to the minus epsilon of k1 times time, minus epsilon of k2 times time, minus epsilon of k3 times t minus delta t times I. If I want to prepare my wave packets such that they scatter with some separation, delta t, this is what I should do. Now my wave packet for particle 3 moves, but it meets the value 0 with some delay. And I should prepare the state like this, times the wave function that I would write of P1, P2, P3, N1, N2, N3. Okay? And now something very cute would happen. What would happen is that you would have a couple of regions. We have region A, we have region B, we have region C, and we have region D. Okay? And what you would see is that in A, you would start in A, and in A, only the incoming wave would have a support. If you write the 3 equations that you get for K1, K2, K3, and see, can I solve them? You find that only A is supported there. Then you go to region B. And in region B is after, no, region A, and region B is after 1 and 2 swap. And you resolve the equations, and you see that in region B, only this plane wave is not suppressed, which makes total sense. Now the state evolves, and after this time, particle 1 and 2 scattered. And then you go to region C, and in region C, you solve again the set of the equations, and you see that only the one where particle 1 meets particle 2 and 3, you can solve. So only this one contributes. And then you go to the last region D, and in region D, you see that the only wave function that contributes is the ones where all of them scattered. So in this way, we measure in a time evolution 4 of the 6 terms of the wave function. What about the other 2? Can someone tell me how would I measure the other 2? Sorry?
Will they cancel?
No. So what are the other 2? The other 2 that we are missing is this one and this one. Let's call this B prime and C prime. This is what you would get if you would prepare not with a time advance but with a time delay. If you would prepare this line to be here, that is if you prepare delta t to be negative, then first 2 scatter with 3, then 1 scatters with 2, and so on and so forth. So this is what we would get for delta t negative. So by preparing this experiment, where you prepare the wave packets to scatter in this particular way, you can really measure all the coefficients of the wave function. As you are evolving in time, the different wave functions that are localized are changing, in perfect agreement with our intuition that whenever we swap 2 particles, we pay the corresponding S matrix. And this is how we understand. We just prepare the state that indeed we see that we start with these exponentials, then we get after a while P1, P2 gets swapped and it pays an S matrix, then P2, P3 gets swapped and we pay an S matrix, and then the other 2 get swapped and we pay another S matrix after some time. And this is how you connect time-independent Schrodinger equation with time-dependent Schrodinger equation. And it's always the same thing. If you have, say, an incoming wave, it scatters through a target, and then there is a spherical wave. You again convolute by a plane wave, and then you see that a spherical wave only has support if time is positive, and so on and so forth. And this is always how one makes contact between time-independent Schrodinger equation and time-dependent, and how we make contact between stationary states and real-time scattering. I think. At least this is how I understood it. Okay. So, cool. Let's continue tomorrow.